So here we're going to talk about linear systems. So we'll start with the definition of a linear equation. A linear equation in n variables is any equation that can be written in the form a1x1 plus a2x2 all the way up to an xn, which is equal to b. All of those a's should be constants as well as the number b, and then the x's are going to be variables. So just a few examples of linear equations. We can have 3x1 plus 2x2 minus 7x3 minus x4 is equal to 4. So this one has 4 variables. And you can have as many variables or as few as you need. Another example, ln of 4x1 plus 7x3 is equal to minus 6. So this one has 3 variables. While you only see 2 of them, x1 and x3, we can tell that this has 3 variables because the largest number is 3. The x2 just has a coefficient of 0. Another example, 4 over 7x1 minus 1 over 3x2 plus 9x3 equal to 0. This one also has 3 variables. One last example, 0.8x1 plus 0.2x2 is equal to 9. So all of these are examples of linear equations. So these are actually all written in the standard form as well. So we'll also give some non-examples. What are equations that are not linear? Well, we can have 3x1 raised to the 4th power plus 2x squared minus 7x3 is equal to 1. So this one is not a linear equation because of the exponent. The variables should not have any exponents on them. Another example, 8x1 minus 2x1x2 plus 3x3 is equal to 2. So this one is because of the multiplication of the x1, x2 that makes it nonlinear. A third example, 9 square root of x1 minus 6x2 plus x3 equal to 0. So this one is not linear because of that square root sign. And then one last example, 6 sine of x1 plus 2x2 equal to negative 5. And this one is because I have a variable inside of this sine function. Now that we've defined a linear equation, we'll discuss a system of these linear equations, also known as a linear system. So this is a set of m equations in n variables. So the idea is, now, rather than just an equation, we have this set of equations. And each one should be linear, and we want to solve all of these at the exact same time. So an example, 4x1 plus 6x2 minus 5x3 equal to 1. x1 minus 5x2 plus 9x3 equal to 3. 2x1 plus 7x2 plus 3x3 is equal to 8. So this is a system of 3 equations in 3 variables. This is considered square because we have 3 equations and 3 variables. However, not all linear systems have to be square. For example, if I have 2x1 plus 4x3 plus 7x4 minus 5x5 minus 3x to the 6 equal to negative 4, and then a second equation, x2 minus 3x3 plus 9x5 plus x6 equal to 9. Now this one is two equations in 6 variables. So this one is not square, but it's still a linear system. So the next thing we'll talk about is solutions. It doesn't help just to have a linear system, we need to know the solution. So a solution of a linear system of n variables is an n-tuple, S1 through Sn, such that when Si is substituted for xi, each equation becomes a true statement. And if we deal with all possible solutions, this is known as a solution set. So the idea here is to just what works in every single equation. So for example, is 4, -7, 0 a solution of this given linear system? Well, let's see. We have 2x1 plus 2x2 minus 8x3 is equal to -6. So the idea here, we should substitute this given point in for x1, x2, x3. So 4 is x1, -7 is x2, and 0 is x3. And now we just need to see if this gives us a true statement. Well, this is 8 minus 14 plus 0 equal to -6. And we can see that yes, that is true. However, that's not enough to determine if this is a solution. We need this to work in all 3 equations. So 3x1 plus x2 minus 4x3 is equal to 5. Substituting the point in, 4, -7, 0. And then we just need to actually work it out. So this is 12 minus 7 plus 0 equal to 5. And we can see that is also a true statement. So now we just need to check the third equation. -x1 plus 3x2 plus 7x3 equal to 0. So sticking in 4 for x1, -7 for x2, and 0 for x3. This gives us -4 minus 21 plus 0 is equal to 0. We can see that that's not true. So is this a solution? No, it's not. In order to be a solution, we would need this to work in every single equation. Once we get one equation that it doesn't work in, we can say that it's not a solution. So what can solutions actually look like? Well, it might be easier to think of it in terms of lines. If I have 2 equations and 2 variables, the only thing that is just 2 lines, and the solution would be their point of intersection. Well, this has 3 possibilities. I could have 2 lines that intersect at a point, and this point would be the solution. So that would be one solution. However, it's also true that the lines could be parallel. In this case, they have no point of intersection, so there would be no solution. And then finally, I could consider the same line twice, in which case they intersect at every single point on the line. So we would have infinite solutions. And while we demonstrated this using lines, this can actually be expanded to every system of equations. It will either have one solution, no solution, or infinitely many solutions. So now that we've defined what solutions can look like, what do we call them? Well, a linear system with at least one solution is known as consistent. And the opposite of that, a linear system with no solution, is inconsistent. If we have no more than one solution, it's known as independent. And a linear system with more than one solution is known as dependent. So these are a lot of definitions, but we can organize them and see exactly what's going on here. So let's make a chart. On the top we'll have independent and dependent. And then on the side, consistent and inconsistent. And we'll look at the different possibilities with each of these. And we're just going to abbreviate here. So consistent means we have at least one solution, and independent means no more than one. So the only thing that's greater than or equal to 1 and less than or equal to 1 is 1. Consistent means at least one, and dependent means more than one. So the only way to have more than one solution would be to have infinitely many. Inconsistent would be no solutions. Independent means no more than one, so this would be no solutions. And then the fourth option here, inconsistent means no solutions and dependent means more than one. It's impossible to have none and more than one. So this one is impossible. And so this gives us a little bit more of an organization into these definitions.